Okay, the next test that we're going to learn is in section 11.5, and this is called the alternating series test. So like the name says, this will be used on what we call an alternating series. This is the only time when this test would be applicable. It doesn't necessarily mean that you have to use this test on an alternating series, but that's when you would think about it. So what is an alternating series? It's kind of it's almost like a self-defining term, but I'm going to write a definition down. An alternating series, it's a very easy concept, is a series whose terms, the things that you add up, alternate positive and negative. Positive and negative. Okay, so we've mentioned this before. I'm going to write a couple of these things down. What you'll see is this device attached to some other quantity, I'm going to just call the other quantity Bn, right? This would be the pieces that generate the numerical values. This is a device which just switches the sign. This creates the alternating between positive and negative. And if you look at this case, if n starts at 1, this will start off negative. So this would go negative, positive, and so on. It doesn't have to be the case. So, this is one example of an alternator. Say you want to start positive, then you can adjust the exponent like that. So when n is 1, we'll start off squaring the alternator and you start positive. And you can have this as n minus 1. There's obviously no restrictions on that. But this is typically what you might see. So this is a relatively easy test to implement. I'm going to write out the test. I'm going to abbreviate here AST. And there's a disclaimer. Well, I wouldn't call it a disclaimer, but we have. Let me rephrase that. There's two conditions. If one Okay, what this indicates is that the terms, the things you're adding up, are decreasing. This means decreasing, but this is actually means eventually decreasing. So what that means is the first 2, 3, 4, 200 terms could actually increase, but at some point you hit a point where everything after that is decreasing. Okay, so that's condition 1. And 2, I want to add something here and make this a little better. Put this up here. I'm going to put what I just had on the last page. So what I'm just saying is, given an alternating series, and the Bn that we're addressing here is the numerical part. It's the part without the alternator, right? It's just what's generating the numbers. Okay, so that's the. I'm glad I put that. I should have put that first. So if these numerical values are eventually decreasing, and number 2, if those numerical values go to 0, then the series converges. Okay? So again, you're given an alternating series. In our analysis, we're gonna ignore the alternator. We're just gonna look at the piece of the puzzle that provides the numerical values. If they meet these two conditions, this series converges. And those conditions are that the terms are decreasing eventually, which this doesn't come up a lot, but it needs to be added for precision. And if those terms go to zero. Again, an important point of this, similar to the divergence test, is that this only can show one thing. It can only show convergence. So if one of these conditions fail, the test has sort of failed. It's inconclusive. So we're going to add as a note here, cannot show divergence. So it's another one of those one-directional tests. Okay, so I'm going to go through some examples and make a few points about the mechanics of doing the problems. Okay, so a nice straightforward example would be something like this. Again, it's the same question. Does it converge? Does it diverge? And you're going to see the alternator in plain sight, so that's an indication that this is a good test to try. It doesn't mean that this is necessarily, that's a n cubed plus 1. That doesn't necessarily mean that this will work, but it means it applies. So I'm going to actually do the two conditions in reverse order of what I've shown, but this is the Bn. Okay, this is the part that generates the numerical quantity. For the analysis, we ignore the alternator. So I'm going to evaluate the limit of this thing. And I mean, this is almost a no work problem, right? We have a degree 3 greater than degree 2. The limit is 0. So that condition, I know that just by looking at it, but I want to write it, of course. Some limits require a little bit more work, but this one is straightforward. And now I got to check the this is the sticky part, and I'm going to. It's clear to me that this is decreasing for the same reason. The power on the bottom is greater than the power of the top, so the bottom is growing at a faster rate. So I make this statement, but I always need to provide some form of justification. Just to write this is not enough. And I'm just going to make a simple plain English statement that the degree denominator, and I'll abbreviate here, exceeds degree numerator. I need some justification. You know what else numerator. Something I left out. I need to state the test. And it's fine with abbreviations are fine. I abbreviate AST. Keep that in mind for any problem you're going to do in this chapter when it comes to the exam. We need to state what we're doing. State what you're doing, do it, conclusion. Okay, so this is the work, and this is really provides the conclusion. Both conditions are met, so this series converges. And you know, you're going to see a lot of them are not much more difficult than this. You could make some that are a little bit crazy, but you could say that about just about anything. Oftentimes you're going to be comparing powers. So let's see. I'm going to do one that I would say is considerably more difficult, just so you can see. You know, I don't want to do 5 of the same problems essentially. Actually, you know what? Let me back off. I'm going to back off that for a second. You could have problems. This one is not that example. But rather than create another example, I'm going to stay with this one. This is clear that it's decreasing. If it's not clear, let's just say that it's not as clear as in that example. What you could do, and I'll do it for that one. Not that you would do it for this one. But what you can always do to show decreasing is to consider Bn. And if I think of this as a continuous function, how can I decide if a continuous function is decreasing? I can check the derivative. All right, remember that? So let's see what this would look like. If this is a continuous function, I'm just going to call this b prime. I'd have the bottom derivative of the top minus the top derivative of the bottom squared. Okay, let's clean this up a bit. So I have 2n, yeah, that works. 2n to the 4 plus 2n minus, what do I have, 3n to the 4? I have a couple like terms. So I have negative n to the 4 plus 2n. So this is a nice derivative. I'm going to factor an n, and I'll have 2 minus n cubed, let's call it. Now why did I do that? Keep in mind n is always positive, right? N starts at 1, 1, 2, 3, 4, etc. So this is always positive. This is a square. This is always positive. And then once I get to n equals 2 or greater, this is negative. So this is actually showing that this is decreasing by showing that if this is a function, it has a negative derivative. That indicates the values are decreasing. That's a Calc 1 issue. Remember that? So if you the point being this, and again, you wouldn't do it for this problem, but if you have something that's a little bit more sophisticated where you can't just make a statement like that, in my opinion, and I hate to use this word, you can consider this obvious if you make the statement. If you have something that's not obvious, and I know there's gray area, so you know you can ask, but if it's a little bit more sophisticated, you can always go to the derivative. Okay, negative derivative implies decreasing. Now I want to show you, and I want to just come back. I'm going to make this point again. I don't mean to sound like a broken record, but when you do these types of things, you want justification. Okay, you also want to name the test. So remember, what am I going to do? Do it. Conclusion. It's very, very important for full credit. Now, what happens if this doesn't work? And I'm going to give you a hint. I don't know, something that maybe the book doesn't really let in on. Let me see if I can find them. I want to find a special. Okay, this looks like a good one. So we're going to have an alternating series. So I think in my head, all right, this might be a good candidate. This has. No, that's not a good one. Give me a second here. Okay, this is a good one. This is an alternator, right? And now I have, and this is not really that much different than previous. So I want to dive in with the alternating series test. And the first thing I know is that, again, this is Bn. I have equal powers this time, 1 and 1. So this limit is 3/4. So this test fails. And this is a hint. Excuse me. If the test fails, your go-to is most likely the divergence test. Now, if I'm going to do the divergence test, I'm taking the limit of the entire term. So let's examine that. And my claim again with the divergence test is if this does not equal 0, I've shown divergence. Well, think about what's happening here. This basically is proven it. This piece is going to 3/4. This piece is just flip-flopping between 1 and -1. So the limit here, it doesn't exist. At the end of this, it's going between numbers like +3/4 and -3/4, right? This is going to 3/4, and this is flip-flopping that sign. So this limit doesn't exist. Well, if it doesn't exist, it certainly doesn't equal 0. So this diverges. So that's a common approach to an alternating series. You start out and if the test works, it works. Congratulations. If it doesn't work, then you try the divergence test, and essentially it's likely that the work is essentially done, because this is the limit without the alternator. What's the alternator going to do to that limit? It's just going to make it flop back and forth. Okay? So a lot of the homeworks will probably feel this very much the same, but again, this is only to be used on an alternating series, as the name indicates. It doesn't mean that you have to use it on an alternating series. There are a lot of these problems that can be done with multiple ways. Not all of them. It doesn't mean every problem can be done any way, but a lot of them can be done more than one way. Okay? Thanks.